Okay, this is the first day of graph characteristics, and we'll just rock on. Okay, this is just a quadratic graph, x squared plus 5x plus 6. You can go into Desmos and get the graph and graph it. The points that you want to graph are the two x-intercepts, the vertex, possibly look at the y-intercept, and I just did this one because it was in the same vicinity just to get the shape of it. So just go into Desmos, get yourself a few points and plot them and get the lay of the land, the way it looks. Okay, this graph opens up. The way that you know that is if you go in Desmos, it's pointing up. That's one way. But the other way to know is that x squared is positive. As long as the x squared term is positive, the graph is going up. Now, to do the domain, remember this is what we did before. We had infinity here, negative infinity here, and negative infinity here. And we labeled our arrows. So this arrow is infinity, infinity, and this one is negative infinity, infinity. So now we can set about looking at our lowest. If you label all those points, your lowest x value that you see on the graph is negative infinity, and the highest one is infinity. And it will be labeled if you label your arrows. So the domain is negative infinity to infinity. And any parabola, any quadratic function, all of them, unless they're real world, will have a domain of negative infinity to infinity. Okay, the range here goes from the lowest y value, which is 0.25 or 1/4, and you can find that on Desmos. So my lowest y value is 0.25 to my highest y value is infinity. So I labeled that. My x-intercept and my y-intercept, my x-intercept's negative 3, 0, and my y-intercept's negative 2, 0. I'm sorry, both are x-intercepts. My y-intercept is 0, 6. And then the zeros of the function, of course, are where the graph is crossing the x-axis at. So negative 3 and negative 2. And the vertex, again, look on Desmos and hover on that point, is negative 2.5 and 0.25. And that is a minimum point. Okay, doing the next one. Oh, I forgot that I did this. Okay, so if we want to find the vertex algebraically, the vertex, this formula here, negative b over 2a, will give you the x coordinate. Also, if you go into mode 5.3, remember I taught you this yesterday on your calculator, the x value, the third thing that pops up will give you the x value of the vertex. So it will spit that out for you. All right, but if I do negative b over 2a, my b term is negative 4. So negative 4 is positive 4, and 2 times my a term. So 2 times 1 is 2, and that gives me 2. So that's my x value. Then to find the y value, you plug it in. You just substitute in. So 2 squared is 4. 4 times 2 is negative 8, negative 12. That gives me negative 16, and that's my vertex. That's how you do it algebraically. Remember, your calculator will do it. Desmos will do it. Go into Desmos and you'll be able to easily see what your vertex is. So, but this is just a third method. Okay, now we have this graph, and again, go into Desmos. I'm not switching between Desmos and this for today's video, but I will when I teach this in class. I will go back and forth from Desmos to this, but I went ahead and sketched your graph. There it is. This one opens down. As you see, my x squared is negative, it's going down. So my domain is going from negative infinity to infinity. My x-intercept is the point negative 5, 0. Again, look at Desmos when you graph it, and also have one at 1, 0. So I have x-intercepts there. My y-intercept is the point 0, 5, right here. And so my zeros, remember, they're the x coordinates of the x-intercepts. So negative 5 and 1. And then my vertex is the point negative 2, 9. Okay. Now this is a real world example. Whoops, gotta get it where you can see everything. Now, I didn't pick the best equation for this because it goes off the graph grid to graph the top of it. So, but it doesn't matter, I just estimated it. So my vertex is at 0.9 and 18, and both of those are estimations. And then I also graphed this point and this point on there. So, and I wrote it down right here. My x-intercept is negative 0.125 and 0, or negative 1/8 and 0. And then 2, 0, that's these points here. My y-intercept is the 0.04. My vertex, again, is that 0.9 and 18, or I took the calculator and I went into mode 5.3 and looked at the last two numbers. That's 15 over 16 and 289 over 16. Now, you can make them, and I just rounded this here, that 18. You can make them fractions or you can make them decimals. It doesn't matter to me. They both work. All right, the domain, this one is going from, in all honesty, now, if this were just a graph of any kind, it would be from negative infinity to infinity. But because this is a ball tossed in the air, you don't have negative infinity seconds. This is the time, and f of x is the height of the ball when you toss it in the air. So really, in all honesty, the person tossing the ball is tossing it from 4 feet. That's what that means. So the domain is actually going from 0 to 2 when it hits the ground. All this right here, when a ball hits the ground, it stops. It doesn't go down into the earth. So it's done. So the domain here is going from 0 to 2. Remember, domain is x. And then my y, my range, is going from 0 to 18, because it's at, if this is the point 0, it's going from 4. Sorry about, no, here's my 0, I'm right. So this is going from 0 to 18, which the 18 is really 289 over 16, but that's your range. So this is a real world problem, and you have to be careful with real world, okay? So in all honesty, would I have this x-intercept in the real world? No, not in the real world. This one right here would go away because we don't have negative time. We either have the time or we don't. So in the real world, there's only one x-intercept, which is right here. Okay. Just making sure you understand that. You're going to have a real world problem with your classwork today. Be careful and read it and think about the fact that there is no negative time and there is no negative. You can't go down, you can't go down below the ground. Now, I think the one that you have has got water in the ocean. So you can go down into the ocean, but be thinking about the real world.